Welcome back everyone, my name is Pedram and this is where we do advanced time series analysis, deep forecasting. Alright, module 3, exponential smoothing. As I said earlier in the previous video, we're going to do this module in 4 lecture videos. The first one was introduction, the second one we went over exponential smoothing methods, and this is the third one that we're going to cover exponential smoothing based models, namely ETS models. And in the very last video, we will do the Python part. All right, this is a summary of what we covered in part 1, exponential smoothing methods. We said, depending on how you want to model trend and seasonality, let me actually write it down. So trend, seasonality. We may end up with different methods, right? So for trend, we can have no trend, we can have additive or additive damped. For seasonality, we can have no seasonality, additive seasonality, or multiplicative seasonality, right? So this here gives you 9 different combinations of different methods that we can apply based on what kind of data pattern we're observing, right? So if in the data pattern there is no trend, no seasonality, we're going to go with simple, let me actually use my laser, we can go with simple exponential smoothing. Then we can go ahead and add a linear trend to that, if you believe that there's a trend, right? And we said, what if that trend is not going to go linearly into the infinity? What if you want to damp it, right? So we add a damped version of the trend. And then finally, we added seasonality, right? So we said we can use Holt-Winter method to control for both trend and seasonality into the future. And finally, we could damp that Holt-Winter trend into the future, right? So these are 6 different combinations that we specifically talked about. We looked at the formulas in the previous videos. And I just want you to be aware that the combination of these methods are not limited to the 6, right? So theoretically, we can actually, we can think of a multiplicative trend as well, right? So in the textbook, we don't talk about it, or in the lecture videos, we didn't cover it. But if you do it in Python, you will see that when you're using a skTime Python package or PyCaret, there's this option that you can have a multiplicative trend as well. This rarely happens in reality because if you have multiplicative trend, the trend is going to become exponential. We don't see time series like that. So for that reason, we didn't cover it. And more practically, when you have something like that, you would be better off if you transform the data first and then simply apply additive or additive damped trend to that. So that's why we're not interested in covering that multiplicative trend. All right, so this was our exponential smoothing methods, which at the end of the day gave us some point prediction, right? Point estimate. So we use a forecasting equation here on the right hand side. And these forecasting equations were able to give us some point estimates into the future. So for example, this is your time series, and those methods are going to give us some point estimates into the future. So it didn't give us anything about prediction intervals, right? So at the end of the day, let me use another color. This is what these methods gave us, and what we're looking to find in this lecture video is that what if you want to come up with a confidence interval, I don't know, 90%, 95%, 85%, you name it, for these predictions, right? So this is where we have to go from exponential smoothing methods to models, and let's see how it's done. So without further ado, module 3, part 2, exponential smoothing based models, namely ETS. So again, these models are going to enable us to come up with not only point forecast, but prediction intervals. So exponential smoothing and point forecast. As we said earlier, these exponential smoothing methods, these are simple mathematical equations which generate point forecasts, right? So here's an example. On the left, you're seeing Australian domestic tourism. This is quarterly data, and from 2000-ish to 2020. Look at that. Imagine this is our data. Obviously, we're going to use a model, Holt-Winter model, probably, right? And the seasonality can be either additive or multiplicative. And if you do that, so here are the point forecasts, how they're going to look like, right? So our point forecast is going to be something like this. So both for additive and multiplicative, they're pretty much close to each other. So that's what the exponential smoothing methods is going to generate. However, how can we extend it to a model that can generate prediction intervals, right? So we need statistical models that generate the same point forecast. So the point forecasts are going to be pretty much the same. So let me use red. So we're looking into this part. And as you can see, the point forecasts are pretty much the same. But on top of that, it's creating some prediction intervals, right? So these shaded areas, these are our prediction intervals. And obviously, if you want to be more confident, if you want to go 95% versus 80%, then you know that these shades are going to get wider and wider, right? So these models are going to produce the entire forecast distribution. So the idea is that if somehow we can estimate the variance of these point forecasts, then we can leverage those variances and create prediction intervals. So the goal is to come up with an estimation technique with a tool that we can figure out what is the variance, what is the standard deviation of those point forecast errors. All right, so let's see how it's done. Before we get into the details of the ETS models, let me clear out some terminology. Specifically, let's talk about state space models. So the ETS models, sometimes we refer them as state space models simply because these are models that describe, let me actually use my pen, how the unobserved components, or we call them states, change over time, right? Remember, in smoothing equations, we had levels, trend, seasonality, and we were keeping track of how they are changing over time, right? So that's why we can also call these things state space models. So we can label each state space as ETS, and we can show them with three different components, right? So E stands for error, T stands for trend, and S stands for seasonality, right? So that's why we call these things ETS. So you have seen the trend and seasonality before, right? We said there are 9 different combinations for the two, and now the new thing is the error thing, right? So this error part is the new part, which is going to enable us to produce that forecast distribution. Remember, if I have a time series like this, with modeling trend and seasonality, we can come up with point forecast, right? And now we are adding this error to enable us to create some prediction intervals as well. So let's talk about the details of this error, how we can add it to the model, and then how we can basically formulate it. So for each method, there exist 2 models, one with additive errors and one with multiplicative errors. So here are different combinations for ETS models that we can have. Again, the trend and seasonal component is not new. We have already seen 9 different combinations. Trend can be non-additive, additive. Damp, seasonality can be non-additive and multiplicative. This is a new part, right? So we had 9 different combinations previously. Now we need to multiply it by 2. We can have 18 different state space models for each of the exponential smoothing method, right? And guys, there's nothing fancy here. This all says that depending on the pattern in the data, you can come up with one of these realizations, right? One of these combinations. So for example, if you have a data set like this, which is showing seasonality and upward trend, and actually for I'm going to show you that this is a train set. Let's say this is your test set, right? Imagine that's it, right? And the red one is your train and the blue one is your test set, and you want to make some forecasts. So obviously you can say, the answer for this one, you have to have an additive component for trend. You have to have it maybe additive or multiplicative seasonality. Here in this case, we can say additive component for seasonality. And then for the error, don't worry about it too much. We're going to see the formulas, and then we can see should we do additive or multiplicative, which one is going to work better, right? But here, I'm going to just make sure that you understand the difference between error and residual, and you do not confuse these two things, right? So what is residual? Let me actually write it down. Residual. Residuals are your yt minus y hat t. So this is pretty much the same for all the econometrics model. This is how we define residuals. And in ETS, in exponential smoothing methods, we define them as ET, right? And then here, let's say let's use a very simple exponential smoothing method. And in the test set, imagine this is my, this is my SES, right? In the test, you know that it's going to be a simple level, right? That's what we talked about in a previous lecture video. So now here I can say, for example, we are here. This is the observation, right? This is my yt, this is my y hat t, and the difference between the two, this is going to be my residual, right? So we have residual at point 1, residual at point 2, residual at point 3, and you name it in the test set, right? Now we can say, and as you can see, this residual is observable, right? So let me actually write it down, observable. These are really important points I want you to pay attention. So these residuals are observable. And then because they are observable, there is no point of uncertainty here, right? In order to add a level of uncertainty to the models, to the exponential smoothing methods to make the model, we are going to make some assumptions, right? We say that these residuals can be assumed to be normally distributed, or a combination of that is going to be normally distributed. So that's exactly what's going to give us if the errors are additive or multiplicative. So again, don't worry about the details. I'm going to use the whiteboard and explain all the details in the future, next slides. But at a high level, when we say that we can add the errors in an additive way, so this is errors. Again, it can be additive or multiplicative, right? Additive simply means that, your errors, we're going to show them with epsilon. They're the same as the residuals, but we're going to make a huge assumption for that residual. We're going to say they are normally distributed with average 0 and standard deviation or variance sigma square. Okay, so this is, and for additive, we're going to say basically they're the same, right? Epsilon t is going to be yt minus y hat t. So this is your additive. Multiplicative is slightly different. Instead of looking at the residual, we look at the percentage version of the residual. We say your epsilon t is going to be equal to yt minus y hat t divided by y hat t. You're going to see why we do that, why sometimes it's going to work better. But the idea is that this is a big assumption we're making, right? We're assuming that, here, look at that. We're assuming that this residual is normally distributed. And we know that in time series, that's not necessarily the case, right? Especially because of the time independence, temporal relationship in the data. And the idea is that what if you want to make this assumption less strong, right? So we say, okay, the percentage version of those residuals is normally distributed. And that typically holds more realistically. It's a less strong assumption, right? But this multiplicative errors come with a caveat, and the caveat is that it only works when the data is strictly positive, right? Because if you have zeros or negative numbers, this thing is going to explode, and then obviously it's not going to be normally distributed, right? And it's going to be less stable. So at a higher level, just remember, we have two components, trend, seasonality. We can add them in 9 different combinations. Now we're adding this new thing, the error thing. And the error thing can be added to the model in an additive way or multiplicative way. Additive way simply means that the difference, yt minus y hat t, is normally distributed. Multiplicative is this. Again, I'm going to write down the formulas and we'll see why we call it additive and multiplicative. But why do we care about this epsilon t? Because at the end of the day, this is something that we can estimate the variance of the forecast errors. And based on these variants, we can come up with prediction intervals. That was the whole point of why are we doing this, right? We want to come up with prediction intervals. So if I'm talking about my SES, the prediction interval for SES is going to be something like this. Okay. Now, in the next 4 or 5 slides, I'm going to use a whiteboard and try to refresh your memory how we started estimating the parameters for SES, simple exponential smoothing. And then we're going to move on to models, how we can come up with estimating these errors here. Basically, let's see. The variance of these errors, and then how we're going to use them to come up with prediction intervals. So I want you to stick to the high level and don't get lost in the mathematical equations. And this is going to be a little challenging for some of you guys, but just hang in there. Maybe you need to watch this part of the lecture video multiple times, but just watch it non-stop through the end of the lecture video, and then come back and watch it again. All right, in order to connect the dots for you and basically explaining what is different between these methods and models, I need to start from very beginning, start from scratch. So let's go back to our SES method estimation. This is what we covered in the last lecture video, but here's a very quick review of that. So what are we doing in these methods? Let me actually write down the method. We're coming with point forecast, right? So at the end of the day, our point forecasts were something like this. We said, okay, y hat t plus h given information at time t. This is our terminal point, right? So, and again, these methods were able to give us the point forecast, right? Now our goal is to use some model to come up with prediction intervals. So goal is come up with ETS models that not only give us the point forecast, it's going to give us, so point forecast plus, let's see, point forecasts plus prediction intervals. So this is what's the difference between our methods and models, right? So prediction intervals. So basically it's going to give us those y hat, the same point forecast. They're going to be exactly the same. You're going to see in Python that either if you use exponential smoothing methods or ETS models, the point forecasts are exactly the same. And then plus, this is a new part. This is our prediction interval. And the prediction interval is what? It's simply, your point forecast. Let's say y hat t plus h given t plus minus some notion of uncertainty here, right? So we have confidence. This is our critical value. So for example, for 95%, this number can be 1.96 for 95%, right? And then we need to multiply it to some uncertainty, right? So this is, I call it sigma h. So these are the forecast errors, right? That which depends on the, of course, time horizon as well. So if you wish, later on, we're going to model this thing, sigma h is equal to a function of your sigma square. So this is forecast errors. And basically, we're looking at the variance of forecast errors and a bunch of parameters. So the parameters can be alpha, beta, gamma, phi, you name it. You have seen all these parameters in the previous lecture video as well. Okay, now going back to our SES, right? So this side. What did we have? We said a simple SES, simple exponential smoothing model. We had our forecasting equation. We showed you y hat t plus h given t was equal to some levels, right? We said basically, we have, at the end of the day, SES is simply just coming up with a level. What is that level, right? And then with a bunch of exponential smoothing equations as well. So here we only had one because we only had level, and the exponential smoothing equation for that was alpha yt plus 1 minus alpha, again LT minus 1. It was a weighted average of what we have for actual observation today, plus what was our previous level, a weighted average of the two, right? And then, so let's see. Then we said, okay, how we estimate these parameters, right? So the parameters of the SES model were your initial level and alpha, right? How did we estimate them? We said, okay, let's go ahead and define the residuals. And remember, these residuals are observable. So residual at point 1 was what? Was y1 minus y hat 1, right? y1 is given, this is actual data. Your y hat 1, your y hat 1, we are going to bring it from here. So this is our fitted values. Y hat t is equal to LT minus 1, right? So we have seen these things before. So we will come up with something like this. y1 minus LT minus 1, which is L0, okay? So this is your E1 or error 1. Then we have this one. Then what is E2? So it's y2 minus y hat 2. So basically it's going to be your y2 minus y hat 2 is L1, right? So, and then we say, okay, L1, we don't have L1, so we have to use this equation to come up with L1. So your L1 is going to be equal to alpha y1 plus 1 minus alpha L0, right? So now you can see, given L0, so we are going to say, given L0, we can get L0 and alpha. We can come up with these numbers, right? So what is epsilon 1? What is epsilon 2? Well, let's go E1, E2, E3, you name it, right? E3 and etc., right? So why do we care about these things? Because eventually we can put them together and make a loss function, right? So our loss function can be something as simple as, sum of the square of these errors, right? So basically we can say, the summation of these errors to the power of 2. We can call it ET. T goes from 1 to capital letter T. We're training this, right? And then we can minimize this loss function. I can go ahead and say minimize this. We are minimizing this thing over the parameters. The parameters are L0 and alpha, right? So we start from, computationally, we start from some given numbers. L0 and alpha can be anything, right? And then we calculate the errors. Then we minimize the sum of square of these errors to back out the optimal values for L0 and alpha, right? So we come up with L0 star and alpha star. So this is how we identify the parameters of an SES model. So what I want you, why are we repeating this? What I want you to take away is that just pause the video and focus on this parameter identification process. Do we see any source of uncertainty? No, everything is observable. The residuals, again, if I'm using errors just interchangeably, but what I mean is basically residuals, right? These are our residuals. These are observable. We didn't make any assumptions for them, and then we minimize the sum of square version of them to come up with the parameters, right? So as you can see here, what we got is the point forecast at the end of the day. I'm exaggerating here. I'm showing some data with trend and seasonality, and I'm using SES, and you may know that SES is not going to do a good job. So for example, this is SES. Okay, and yeah, so basically with this, we were able to come up with point forecast, right? And do you see that there's no way we can come up with prediction intervals because there's no uncertainty here? How do I know? When did we even talk about the uncertainty in these residuals? Never, right? So that's why we have to go beyond that. We have to say, okay, let's now assume these residuals like this, yt minus y hat t. Let's assume they're normally distributed with these parameters. Mu is equal to 0 and variance is equal to sigma square. Okay. Now we are adding this noise, we are adding this uncertainty to the model. We can call them epsilon. So this is the additive way, right? So now I'm using different terms. We don't use E, we use epsilon. So just say that we are going to make an assumption for that. They come with some uncertainty. And then if I estimate, somehow, if I can estimate the variance of these errors, then I'm done. Then we can say, okay, the point forecasts are this. Now I have some notion of the variance of these things. I can add and remove, well, I can say plus minus some of those numbers, multiply some critical values, right? So this is how we are going to come up with prediction intervals. So hopefully you're seeing that why SES, or exponential smoothing methods, by construction, they're not able to give you some prediction intervals. And we have to make an assumption. With that assumption, we can come up with an estimation for the forecast errors. We use those forecast errors, or the variance of those forecast errors, to come up with a prediction interval. So that's at a high level why we should go beyond exponential smoothing methods if we're interested in prediction intervals. Okay, now let's talk about the ETS model errors details, right? So we said that we can have these errors in additive way, additive versus multiplicative, right? Multiplicative. Okay, so and now let's stick to our simple ETS. Let's write it down, ETS. So here either it can be additive or multiplicative, and then no trend, no seasonality. So this is analogous to our simple exponential smoothing method, right? When your data is something like this, if you believe that the data is something like this, there is no seasonality, there is no trend. And then you think that's the case, and then hopefully this SES is going to be a good model, or ETS, and no trend, no seasonality. Now, additive components, let's talk about the additive component error on the left-hand side, and multiplicative, let's use another color, on the right-hand side. Okay. So here we said that let's assume this yt minus y hat t, we call them epsilon t, and they're normally distributed. Okay, and this is a big assumption. I just want to highlight this. This is a big assumption. So maybe actually write down, yeah, big assumption. And I'm going to tell you that the validity of your prediction intervals is as good as the validity of this assumption. If you believe that your time series is non-stationary, there's very temporal relationship in the data, and then this is not a good assumption, so this is a sign that your prediction intervals are not going to be that valid. Even though you say, yes, 95% prediction intervals, but in reality, what happens is that that's not going to hold. And if that's the case, so this is a sign that your assumption that you started with was not a good assumption. But again, what can we do? You know, we're economists, we have to make some assumptions and then work with that, right? So if you want to relax that assumption, we say, you know what, let's assume yt minus y hat t divided by y hat t. So this is a ratio, right? The odds that this is more normally distributed is higher. Okay, but again, so I can say, and this is still a big assumption, but less. I think I would say more relaxed than the additive version, right? Well, what are the implications? So the implications are like, let me actually write down the equation for our yt, because remember we had, let me use red, we had something like this, right? We had yt is equal to y hat t plus epsilon. So I'm just simply singling out for yt, right? So, and that's basically where the additive term is coming from, right? So yt is equal to, no, some predictions plus some errors, right? Epsilon. And then on this side, what do we have? So I have to write down, I say epsilon t multiply y hat t is equal to yt minus y hat t. So if I single out for yt, what do we get? So we're going to get y hat t plus epsilon t y hat t. So we can simplify it further. So your yt is going to be y hat t multiply 1 plus epsilon t. So this is where the term multiplicative is coming from, right? So this is multiply 1 plus epsilon. This is plus epsilon, right? So that's basically that's the difference. And obviously later on we can, how can we write this down? We can say this thing, you know, your yt, if we are talking about ETS A and N, so let me actually do something like this. ETS additive error, no seasonality, no trend, no seasonality. Our forecasting equation is going to be something like this. Well, actually our yt is going to be lt minus 1 plus some errors. Okay, and then here our ETS multiplicative and NN is going to be what? YT. Because remember, what is Y hat? The Y hat is coming from our SES. In the previous slide, we saw that it was LT minus 1, right? So this is going to be equal to LT minus 1, 1 plus epsilon t. And these equations are the ones that we're going to work with in the ETS models, right? So I'm going to show you 18 different versions of these equations. And hopefully now you're not wondering where those equations are coming from, right? So I can write down another version for LT and LT minus 1. Sure, we're going to do it in the separate slides, but LT itself is going to have an equation. Here, LT is going to have an equation for itself. So we're going to drive those equations, and then this is going to be your ETS model, ETS A and N, and this is going to be your ETS M and N, right? So regardless, if you assume the error is going to be added additive way or multiplicative way, the goal is to estimate the variance of those forecast errors, right? So this is a big deal. This, at the end of the day, oops, let me see if I can reverse it. Okay, so this was sigma squared. Oh, it's giving me a hard time, sorry. So now let me use highlighter. At the end of the day, this is what we're interested in. These two, right? Again, additive or multiplicative. Because if I have that thing, then I have an estimation for uncertainty of the forecast error. I can use that to come up with prediction intervals. Let's see how can we estimate those standard deviation or variance of forecast errors as well. This is going to be another parameter. Remember, in SES, what did we have? In SES, we had, let me actually write it down. In SES, we were supposed to estimate alpha and L0. And now the new thing is this. So in ETS, we're going to estimate these parameters. So ETS, the parameters for the ETS model for A and N is these three: alpha, L0, and sigma square. So this is a new part. In SES, we didn't need to estimate that one. Actually, we were not even able to model it. All right, I think it's coming together. So our last step is to use an engine, use a method or estimation technique that can help us estimate that sigma square, right? Remember, this is the variance of the forecast errors, and our job is to estimate that thing. So the method that we're going to use is called MLE, Maximum Likelihood Estimation. I bet many of you guys are already familiar with that, but here is a very quick slide to remind you what is MLE in a simple term. So maximum likelihood estimation, this is a method used to estimate the parameters of a model based on observed data. Okay, so I know it's a little vague, so I'm going to give you a clear example, a very simple example. Hopefully you can follow. The key idea is to find parameters that maximize the likelihood of the observed data under some certain model assumptions, right? So again, if this is still vague, so just bear with me. Hopefully this example is going to clear things out. Imagine, just for the sake of argument, imagine you know the original distribution of the data is normal. Again, this is a big assumption, but imagine you know it, right? You know that the data, the parent distribution, has an average of 5 and a standard deviation of 1, right? And then, so this is your population. Obviously, the population is unobservable, so unobservable. And these parameters are not observable as well, so this is unobservable. But for the sake of argument, imagine you know the answer already, right? So what you observe in the real world is one realization of this population. What do I mean by that? So for example, at the end of the day, what you see is this is observation number. These are, actual values. So for example, you have a random variable, I can call it X, Y, whatever, Z. So then I have, let's pick 5 observations, 1, 2, 3, 4, 5. So I'm randomly drawing a sample from this population. Okay, just bear with me. All these things will come together. So what are those numbers? Imagine the numbers are, 5.1, 4.9, 5, 4.85, 5.2, and etc. Right? So in reality, what you see, this is just one sample of the entire population. So this is what you see in real world. When I give you a data set, when I give you a CSV file, when you see a time series, whatever, this is it. This is one realization of the unobserved population, right? So what can I do with that? So now you have to say, with this information, how can I figure out the actual, well, how can I get as close as possible to these actual parameters, right? So then I would say, okay, so this is what you need. You're going to say, you have to start from some assumption. Let's assume this X is normally distributed with some mu and some sigma square. So again, guys, this is an assumption. This is assumption. Why do we need to make this assumption? Why normally distributed? I'm going to answer that question in a second. Why normally distributed, right? But let's say that's the case. And then I'm going to say, okay, so this means that, so we're making an assumption. We say, okay, now with this, I can come up with some likelihood, right? So before me explaining that likelihood, let me show you a couple of examples, and then you will hopefully realize where's that coming from. So imagine this is our, I'm going to show you 2 distributions, right? So one is this. So imagine this is your sample distribution. Sample distribution number 1. And imagine in this sample, the average is, let's say we have 2 parameters, right? So mu hat, this is the estimated value, is 5.1, and sigma hat is equal to 1, versus, let's use green, that mu hat is 10 and sigma is equal to 1. Sigma height is equal to 1. Okay. So if I, again, imagine you know nothing about this likelihood function. If I ask you a simple question that what is the likelihood, so I call it likelihood 1, that this sample is coming from these parameters versus that this sample is coming from, let's call it L2, whatever, likelihood 2. This sample is coming from this parameter. Which one do you think have from this parameter? Which one do you think has a higher likelihood, right? Look at the number, look at the actual numbers, 5.1, 4.9, 5. So if I assume that mu hat is equal to 5.1 and sigma hat is equal to 1, which one versus mu hat is equal to 10 and sigma hat is equal to 1? Which one has a higher likelihood? L1 is bigger or L2? Imagine L1 is the likelihood of observing these 5 numbers under these parameters versus L2 is observing the same 5 numbers under these parameters. Which one is a bigger number, L1 or L2? Yes, so L1 has a higher likelihood. So basically we say under these parameters, under these values for the parameters, mu hat is equal to 5.1 and sigma hat is equal to 1, L1, the likelihood that the data is coming from this normal distribution is higher compared to this. Does that make sense? So now going back to why assuming this normal distribution, because we have to quantify these things, right? Again, intuitively, you know that the likelihood is higher, but mathematically, how could we quantify that thing? So the likelihood of observing those, let's say, this is the likelihood of observing those 5 numbers, right? So I'm going to show them. So this is our observations. 1, 2, 3, 4, 5. So I want to see what is the likelihood of observing those 5 numbers at the same time jointly, right? So I need to come up with a probability kind of things or density, right? So for example, I would say if this is normally distributed, then we have a formula for this density function, right? So we have a formula for PDF. And the formula is what? Now we say a PDF of, we can think of this as variable given some parameters, mu and sigma. So you have seen this formula before, hopefully. So 1 divided by 2 pi sigma, sigma squared, and then e to the power of minus x minus mu squared divided by sigma, 2 sigma squared, right? 2 sigma squared. So this is going back to the point that I said, why do we care about this normal distribution? Because if you assume that this sample is coming from a normal distribution, you can quantify the density function, right? You can say, this is continuous. You should not think of it as a probability, but just for the sake of argument, this is the probability of observing observation number 1, observation number 2. So if I want to look at the joint probability, basically I need to multiply them, right? I say, so the likelihood is simply the joint probability of these things, right? So I need to multiply, so let's say probability of observing 1, probability of observing 2, probability of observing 3, and probability of observing 4 and 5, right? So we typically show it with this big pi operator, right? I goes from 1 to 5 here, and then your f. Now this is your PDF, right? So let me just write f to keep it simple. Oh, and well, xi with parameters, right? So basically, because I made an assumption about this distribution, we said normal, I could have come up with some formula for density function. And if I multiply those probabilities into each other, it's going to give me the likelihood. So basically, this is going to give me the likelihood of observing these x's under the values for parameters. The values for parameters are mu and sigma. Now I can use this formula and plug in these numbers and see which one is going to give me the higher likelihood, right? So basically what we're going to do, we're going to maximize this likelihood function given the parameters, in this case mu and sigma, or sigma squared, really doesn't matter. Okay, so let's say mu and sigma squared. Okay, so basically what maximum likelihood estimation is doing behind the scene is changing these parameters in order to make sure that the probability of observing this sample is maximized given the values of these parameters. So hopefully this made sense, and then now you can see why when we wanted to talk about ETS models, we had to make an assumptions for the errors. We said errors are normally distributed. Why normally distributed? Because we know the PDF of a normal distribution. Okay, so you can you could say, okay, not normally distributed, another distribution. As long as you know the density function for that distribution, you could use it, right? But the big assumption in MLE in general, maximum likelihood estimation, is that the errors or some random variable is normally distributed, right? And that's what we're gonna do. Again, why we need that normality assumption? Because we know a formula for density function. With that, we can come up with a formula for likelihood function, and now we can maximize this likelihood function to find the optimal parameters. So this is exactly what we're going to do in ETS to estimate. Let's go back to the point 1 to estimate this, right? The variance of the forecast errors. Why do we need the variance for forecast errors? Because we want to make some prediction intervals. So hopefully you can connect the dots now. All right, the last whiteboard. So ETS model estimation. Hopefully you're doing good so far, and hopefully you've been able to follow. If this was too much, just pause the video, take a break, and then come back. Right? We are almost in the last step. All right, so let's go back to estimating the ETS model, and I'm going to stick to my simple ETS. A, additive error, no trend, no seasonality, right? So this simply means that we're assuming epsilon t is equal to yt minus y hat t, and it is normally distributed with 0 and sigma square. And now I know how can I estimate this guy, the sigma square. Okay, so because we said this is normally distributed, I can go ahead and talk about our density function. Density. So the density function is going to be something like this, f of epsilon t, given the parameters. Parameters are mu and sigma, but here we said mu is equal to 0, so we're going to ignore it, so just sigma squared. Okay, so this is our formula we just showed in the last slide, 2 pi sigma squared, and then e to the power of minus, again, the mu is 0, so we can simply ignore it, epsilon squared divided by 2 sigma squared. All right, so this is our density function. With that density function, we can come up, remember guys, these are your errors, right? And we assume that these errors are normally distributed. So basically we have a bunch of them, bunch of those errors here, right? Those are any numbers, positive, negative numbers. And 1, minus 1, 2, minus 2, 1.5, etc., right? So these are a bunch of numbers. And let's say we have hundreds of them, we can come up with a likelihood function, right? The likelihood function is basically multiplication of all these f's or probabilities or densities, whatever you want to call it. So let's say I have 100 of these observations. You have a time series with 100 time steps, so you have 100 of them, right? So I say probability or density of 1 multiplied 2 all the way to capital letter T, right? So this is going to be your likelihood function, and I want to maximize that. So I want to maximize this likelihood function, which is a function of L0, alpha, and your sigma square. Okay, where's this L0 and alpha is coming from? Remember guys, this is your yt minus y hat t. What is y hat t? Y hat t is your lt minus 1. Okay, and inside the lt there's a process. Inside that smoothing process there's alpha and L0 as well, right? So we've talked about it before. All right, so this is going to be maximizing multiplication of a bunch of those density functions, right? So just let me quickly write it down. Again, the same thing, right? So 1 divided by 2 pi sigma square root e to the power of minus epsilon t divided by 2 sigma square. Okay, don't get overwhelmed. This is pretty straightforward. So this is just the ugly formula for density function of normal distribution. Again, nothing fancy here. Now I can open up this epsilons to show you where those parameters are coming from, right? So this is basically your yt minus lt minus 1 to the power of 2 2 sigma square. All right, so now this is it. We want to maximize this likelihood function given these parameters. And remember, these are the parameters of interest. But just a reminder, L0 and alpha are the same parameters for SES model. Now we're adding the sigma square. Okay, so the beauty of this whole MLE is that now we can estimate the sigma square, and then we can come up with prediction intervals based on that. So in practice, basically, how do we do that? So we can go ahead and take derivative with respect to sigma square, set it equal to 0, and then find this sigma square, right? And as you can see, this is multiplication here. In practice, it's a lot easier to work with summation versus multiplication. So that's why we work with maximizing. Instead of likelihood, we do with log likelihood. So I'm simply taking log from both sides, and then this summation, this multiplication operation is going to become a summation operation, right? So summation of 1 through t. Don't worry about these formulas. You don't need to memorize them. Just what I'm doing is simply going from that multiplication operation to summation operation. So this is going to be log, taking log from both sides. 2 pi sigma square, and then minus, again, log of e to the power of something is that something. So basically I have here yt minus lt minus 1, 2 sigma squared. Oops, yeah, the numerator needs to be to the power of 2. Okay, so yeah, this is it. We are maximizing the log likelihood given these parameters L0, alpha, and sigma square. Right? So we're done. So basically doing this optimization, we are going to end up with optimal values for L0, alpha, and sigma square. Okay, so now here's a little details. Computationally, we do it well in Python. We're going to solve this optimization problem numerically. So what does it mean? So let me actually write it down. Python, this optimization, Python. We're going to do it numerically. Numerically simply means that start with the initial values for L0, alpha, and sigma, and then just try to iterate through the formulas and then optimize the values, right? So we have to use some solvers, those solvers, so numerically using solvers. For example, we can do gradient descent, we can do BFGS, so these are different solvers, right? So eventually we're gonna go through iterative process and then optimize these values, come up with an error or tolerance level. If the error iteratively is getting smaller than a certain number, we're going to stop the algorithm and then call it, say, hey, these are the optimal values. Also, we could, so again, this is how it's done. If you're doing skTime, PyCaret, stats model, whatever Python package you're using, it's going to use this thing, some basic gradient descent or a bunch of solvers to figure out what are these parameters. However, let's say, I don't know, when this field was developing, when we were thinking of coming up with prediction intervals, so we wanted to come up with closed form solutions, right? So we wanted to say, okay, so for example, what is a formula for sigma square? What is a formula, right? So you can do that. You can go ahead and say, let's take derivative of this log likelihood with respect to, so derivative of this log likelihood with respect to sigma square, and set it equal to 0, and then come up with a formula for it's a function of something, right? So this is a closed form solution for sigma square. And then we can use these closed form solution to come up with prediction intervals, right? Guys, we can do that. And actually, I'm going to show you a very ugly slide at the end that there are formulas, closed form formulas for the sigma square, depending on what ETS model are we using. That can be, sometimes it can be very long and again, ugly formula. But in practice, we're not going to use closed form solution. We're going to use some numerical methods to estimate these numbers. Okay. So in the very last slide, when I'm showing you some formulas for these sigma squares, don't be confused where they're coming from. So they're coming from simply taking derivative of this log likelihood based with respect to sigma square, and then set it equal to 0, and then solve for sigma square. That's it. All right, that was pretty much it. We came a very long way from the how we estimate the SES methods to ETS models. Basically, at the core of it, how we could estimate the variance of those forecast errors and then later on use them to come up with prediction intervals. So if you followed so far, we're done. So we're done with this module, and then you understand the theory, and the rest is just me going through a bunch of slides from the main textbook of the course, which is Forecasting Principles and Practice, third edition. And yeah, hopefully now when you're reading the book for yourself or you're following the slides, you can understand them better. So I'm going to show the ETS ANN using textbook terminology one last time. But again, we have done this before in the whiteboards. So this is just me repeating everything we said in more formalized versions, slides, and then hopefully you can follow the textbook better as well. Okay, so remember we started from SES components. We said there's a forecasting equation, y hat t plus h is equal to a level, and then there was a smoothing equation for the level itself, a weighted average of yt and previous level, right? We can rearrange this smoothing equation, this LT, to come up with something called error correction form. So we showed it before, right? So the error correction form is LT is equal to, what do we have? Now we are going to say, instead of basically writing something like this, we're going to say LT minus 1 multiply 1, LT minus 1 multiply alpha, and then write it down here. So LT minus 1 plus alpha YT and alpha LT minus 1. So we're going to factor in alpha. So we are going to end up with YT minus LT minus 1. So this is pretty straightforward. By the way, what is it? This is your residual, right? So we call it residual. This is your residual. And then we're going to end up with LT minus 1 plus alpha ET residual, right? So this thing was our residual, is a residual at time t. Remember, and then we said level is what ETS ANN is going to predict, right? At the end of the day, your ETS ANN is going to predict some level. So here, this is your time series, and then this is what ETS ANN is going to predict, right? Again, that level can be here, higher or lower, right? Somewhere between the simple total average and the naive forecaster. So we talked about all these things previously, right? So the idea is that if the model, so I want you to just focus on this thing, the equation for the level components, right? Focus on this one. And you see that if the model is over and undershooting the level, and then we know that in general, the level is going to adjust, right? How does the level adjust? By this parameter alpha, right? So the magnitude of this adjustment depends on alpha. A smaller alpha means a smoother adjustment. So is that, okay, here's the level. And in sample, we can have something like this, right? If it is over predicting, it's going to adjust it lower, and etc. So you get the idea. And then for forecasting horizons to the future, is the flat line because it's a simple level. All right, so remember, we can also write this YT is equal to LT minus 1 plus residual, right? So again, there's nothing fancy here, guys. This is your YT is equal to Y hat T plus epsilon error T. So this is residual. We already know that residual is YT minus Y hat T, right? All right, so at the end of the day, we say each observation is equal to previous level plus some errors. Okay, now let's see how we can use this. So far, let me actually bring all this slide, all the bullet points. So far we show that your YT is nothing but, again, in an ETS ANN, previous level plus some residual, right? So, and then the idea says that the only thing left is specify the probability distribution for errors, right? So with that, we're going to have our first innovation state model. Guys, we said at the end of the day, this is the big assumption, right? Big assumption, and we talk about all the details. So this is additive assumption. We say these residuals are, we call them epsilon, they're normally distributed with average 0 and variance sigma square. And so they're normally and independently distributed. Basically, we're going to say that this is white noise. If you do not like this assumption, you're not alone, because yeah, this is time series, right? So especially if your YT is basically some levels, not percentages, the odds that this assumption is violated is a lot higher. So this means that your prediction intervals are not valid. And that's exactly the case, right? So that's why we're going to see that if your time series I don't know if you can do some transformation at the beginning to make it look more stationary, to make it look more normally distributed. We're going to try our best to do that, right? Simply because the prediction intervals are going to be more valid down the road. All right. So the final model, so again, guys, this is for ETS A and N, and we already saw that there are two equations at the end of the day. One is measurement equation or observation equation, which is your yt is equal to previous level plus some errors, and your state equation. So these are our equivalent to our smoothing equations in exponential smoothing method. So we call them a state equation because this is showing how the unobserved state variables, in this case only the level, is evolving through time, right? So there's a differential equation for that right here. Okay. All right. So that's pretty much it for our simple ETS A and N. We end up with two equations: measurement equation, state equation. You're going to see in the next few slides, I will show you 18 different combinations, and you can pause the video and try to back out a bunch of them. But the whole point is that these ETS models are going to be able to give you point forecast plus prediction intervals. And this is what we're going to see here. There we go. So this is our very own, what is it, airline passenger data sets. Using monthly data, and then as you can see, so let's say this is our train, this is our holdout period, and this is forecasting into the future, right? So, and as you can see, ETS obviously is sorry, ETS ANN is obviously not a good model because it's not respecting trend or seasonality, and these are the point forecasts, and because this is not a good model, your prediction intervals is going to be very wide. All right. Okay, we are done with our very first ETS model, which was ETS ANN. Now, this slide, I'm going to make it optional, and this is optional exercise. For those of you who are interested in derivation of all these formulas, I suggest pausing the video and try to basically back out these formulas, right? So here, this is additive error, additive trends, no seasonality. And you have to remember what we discussed in the previous lecture video when we went over the exponential smoothing methods. It's pretty much the same, right? We say we have a level component, we have a trend component, and h, again, h is equal to 1 if you're doing fitted values. So that's where it's coming from, right? And then I want you to use that, that equation and substitute it in the level equation and trend equation. Try to figure out these things. And it's pretty straightforward. This is just like what we did for ANN, and now you're doing it for AAN, additive trend. And you will, again, for those of you who are curious, you will see that this beta that you're calculating is the same as alpha multiply beta star, and alpha and beta stars are smoothing parameters for level and trend from exponential smoothing methods. Again, this slide is completely optional. I will leave it up to you. But the point is that now, with knowing all the basics, you can back out all the 18 different formulas we have for basically different combination of ETS. And this is how our ETS AAN is going to look like for the same data set, airline passenger. Again, now we are respecting the trend component, but still we are not taking into account the seasonality. So that's why, again, the prediction intervals are going to be wide, because simply this model is not controlling for seasonality. All right, now let's look at all different formulas for 18 different combinations of ETS models. Okay, so this is what I was just talking about, and hopefully, again, we derived only one of them, the simplest one, and you can go all the way to the ugliest one. So don't get overwhelmed. You're not supposed to memorize any of these things. My whole goal was to give you the high level behind the scene of the theory by going over the simplest model, and then hopefully if you're interested you can go ahead and back out the rest of them, right? So remember, so we had two components, trend and seasonality, right? So the trend can be no trend, additive, additive damp. Seasonality can be no seasonality, additive, multiplicative. And this is for if error is additive, right? If error is additive, I'm going to have 9 different combinations. In the next slide, we're going to look at the formulas for when error is multiplicative, right? Again, we were able to drive this one together. And now I left this one as an exercise for you. And then if you're super curious, you can go ahead and work on this one, right? So this is your additive trend. So what is this? This is your ETS, additive error, additive damp trend, and multiplicative seasonality, right? You should be, again, technically, you should be able to back out all these formulas. So this is for additive. This is for multiplicative, right? So for multiplicative, again, we showed this version. So basically, multiplicative error means that you're assuming your errors are equal to yt minus y hat t divided by y hat t. So that was the difference. And then we came up with this for the simplest one, and this is for the most difficult ones. All right, so hopefully now when you read the textbook, when you get to this part, you don't get overwhelmed by all these formulas. I think now you should have a very good understanding at a high level. What are these? Why do we need them? And why do we care about this error in general? Because at the end of the day, this error is this is something that enables us to come up with prediction intervals. So here's a screenshot from PyCaret that we're going to go over the details in the next lecture video. And yeah, one downside of PyCaret is that when you're combining multiple models, you cannot see the prediction intervals at the same time. But technically let me use, yeah, I try to be color coded. So let's use for the red for this one. So technically this is your prediction interval for your ETS AAM, then you can come up with prediction interval for your ETS ANN, and obviously you can come up with another prediction interval for your ETS AAN, right? So in PyCaret, it doesn't visualize them on top of each other, I think simply because it's going to get very overlapped, so that's why. But if you plot them individually using PyCaret or any other Python package for time series, it's going to show you the prediction intervals as well. All right, now let's talk about ETS model selection, because remember guys, we had 18 different combinations, right? ETS, 2 here, 3 here, 3 here, right? 2 multiply 3 multiply 3. So we have 18 different combinations. How can we decide which combination is better, right? So you have to look at some performance metrics in the test set, right? Or in cross-validation. So for model selection, we're going to use either information criteria or cross-validated performance metrics like R-square, MSE, RMSE, MAPE, and SMAPE. So in time series, I'm honestly not interested in R-square. So basically, we're going to focus on, let's say, RMSE. So hopefully you're familiar, you have some machine learning background, you're familiar with the concept of cross-validation. And we basically use cross-validation to come up with an estimated value for the performance of the model in the test set, as well as finding the best parameters and hyperparameters of the model, right? Let's say hyperparameters. So that's one way. Another way is just using information criteria. And this is what Python packages are going to use behind the scene when it comes to model selection for ETS. Because when you're doing PyCaret or SkTime, you simply just write ETS, the model name ETS, and behind the scene is using auto ETS. And auto ETS is looking at a different combination of these components, basically 18 of them, and see which one is giving you the minimum. Well, we're minimizing these metrics, or yeah, basically which one is giving you the minimum value of AIC, AIC corrected, or BIC, right? And that combination is going to be the winning combination. So in all these formulas, they're pretty much the same, but one of them is, for example, penalizing, adding more parameters more strictly compared to the other ones, right? But at the core of them, there is this likelihood function. We are pretty much familiar with that, right? And there's this K is the number of parameters. this is the total number of parameters and initial states as well as the residual variance, right? Your sigma square. So for example, in our SES, remember, oh, sorry, in ETS, this is example, A and N, how many, what was K? K was equal to 3. Why? Because we had L0, alpha, and sigma score. So we have 3 parameters, okay? So this is our example. All right, so the model with the minimum information criteria is the best model for forecasting. So what are we doing here? Remember, guys, this likelihood function is typically between minus infinity and 0, right? So this is minus infinity and this is 0. This is your likelihood function, okay? And we are working with the negative version of that. So we see something like this. And where's the likelihood maximized? Look at that. So let me actually erase this, show you something. Look at that. If the likelihood is equal to 1, so this is log likelihood, sorry. If likelihood is equal to 1, what is log of 1? Log of 1 is equal to 0. So this is where we get the maximum thing, right? So if I work with a negative version of that, what do we want to get? So basically, again, this is typically truncated between minus infinity and that. So that's why I'm going to go ahead and just show it something like this. If we want to minimize this thing, this is log likelihood. I want to minimize this log likelihood. It means that we get to this point where the likelihood is maxed, right? All right, hopefully that makes sense. So why we're minimizing this thing, minimizing the negative version of that. So now we're adding this plus 2k. This is adding penalty, right? If this is something you want to minimize, this means that if you have more parameters, k is going to increase. This whole thing is going to increase. So this is a bad thing, right? So that's why basically adding 2k at the end of this function is going to penalize having more complex models. Having more complex models means that model with more parameters. So model with more parameters like ETS, I don't know, additive damp, and multiplicative, right? So this one has a lot more parameters compared to ETS, A, and N, right? So because it's more complex, it's capturing all the seasonalities, trends, damped version, and et cetera, right? So this is how it works. We're going to penalize this metric by making it, again, if k is increasing, this number is increasing, and it's going to increase this AIC, which is a bad thing because your goal was to minimize that thing. So it's going to give you a trade-off, right? So, and then this is, we call it AICc information criteria, or AIC. We have a corrected version of that when the sample size is small. So this thing is going to correct for the bias of that small sample size. Basically, it's going to be AIC plus a correction term, right? And now, as you can see, we are adding the sample size as well. Here, there's no sign of sample size, which is t. Here, we are adding that t. And then finally, in BIC, this is going to penalize that thing more because we are multiplying this k by log of t, right? So let's say your sample size is 1000, log of 1000 is a large number. So we're going to multiply it by this k. So it's penalizing more complex models more heavily. So again, we can use either of them. I think by default for model selection, the skate time is using AIC, but again, depending on your use case, your sample size, or if you want to be more restrictive, you can do BIC as well. So again, at the end of the day, you have a metric. You're going to minimize that information criteria, let's say AIC, and this minimization is going to give you the best combination of those parameters, right? So out of those 18 versions, the winning one has this. So the winning has minimum AIC. So hopefully now you see when in Python we're gonna do auto ETS behind the scene what it is doing. All right, let's wrap up this lecture video by going over the point forecast plus prediction intervals with ETS models, right? So as we have said multiple times so far, the point forecast can be obtained from the models by iterating the equations for the forecasting horizons, right? So you can say, you can just replace t with t plus 1, t plus 2, and all the way to t plus h forecasting horizon. use those equations for your y hat t plus h and etc. So to come up with a point forecast. So this is pretty much the same as exponential smoothing. And then on top of that, we can come up with, again, as I said, this is pretty much the same as exponential smoothing methods. And on top of that, we can come up with prediction intervals. And for most ETS models, the prediction interval can be written as this. And when I say for most of them, because some of them we cannot come up with a closed form solution for sigma square. But again, computationally, the Python is doing it numerically, right? It's not using closed form solution, as I explained it in the previous whiteboards, right? So we have seen this before. So this is our prediction intervals. Let's call it PI. Basically some point forecast plus minus some critical values. Again, it can be 1.96 for 95%. And then multiply the function of forecast standard errors, right? So again, this thing is going to give us these prediction intervals on the right hand side, and sometimes we can find closed form solutions for these sigma hats. Sometimes it's not, so it's a function of sigma square and all the other parameters, right? Sometimes not. Regardless, in Python, this thing is solved numerically, so we can always come up with prediction intervals no matter what ETS model we're using. But just to conclude this thing and then show everything to you, in the next slide, I'm going to show a bunch of formulas for this sigma hat, for sigma h, depending on what ETS model we're using. All right, these are the ugly formulas that I promised you. So again, don't get overwhelmed. There's no need for you to remember these things. And so for example, look at that. This is our ETS additive error, additive damp trend, additive seasonality, and just the formula for the forecast errors, H horizon into the future is going to be this thing, right? It's not that difficult to drive these formulas, but obviously you can see it's not as straightforward either, right? So for example, we can talk about this one. This is our simple ETS A and N model, right? And then what does it say? It says that is H is equal to 1, your sigma square, is equal to sigma square H is equal to what? Sigma square multiply 1 plus alpha square. Alpha is your smoothing parameter, multiply H minus 1, which is 1 minus 1, so it's going to get 0. So basically, if H is equal to 1, your sigma square for one horizon is sigma square. You can go ahead and try H is equal to 2, and you will see that your sigma square for second horizon is going to be, this is going to be sigma square multiply 1 plus alpha square. Okay, and all the way you can try different H's, right? But what it gives you is something like this. You have a model, and then you have a point forecast, right? So imagine this is a point forecast. Oh, whoa, sorry, this is ANN, so the point forecast is going to be just one line, right? And then in the first, this is H is equal to 1. Forecasting horizon 1, forecasting horizon 2, and etc. So this is your sigma H, sigma square H. This is your sigma square H is equal to 2, H is equal to 3. You get the idea, right? And then we're going to use that formula in the previous slide to come up with these prediction intervals, right? All right, so that was pretty much it, and hopefully you understand the ETS, how ETS models work at a high level. Again, don't worry about the formulas. There's not much value there, especially for those of you who just are interested into the practical aspect of it. But if you're curious, just like me, where are these formulas coming from? Hopefully this lecture video gave you a little bit of understanding. Okay, this wraps up our module number 3, exponential smoothing. We started with methods, and then we extended to models. We call them ETS models. And now we are ready to jump into the Python part. In the last lecture video of this module, I will review everything we did in the past 3 theory lectures, but now in Python. So we're going to do exponential smoothing methods as well as ETS models and all the details of the Python. So some of you guys might be interested in the Python part because this is what you can do in practice, but my personal opinion is that doing these things, these methods, models, whatever you want to call it, in Python is going to become easier and easier and easier down the road, right? So with the help of ChatGPT, Claude, Sonnet 3.5, and etc., down the road, I would predict nothing but simpler application of these models in Python. So eventually we will get to a point that you talk to your computer and then you say, hey, this is a data set, do ETS ANN for me, and it's going to do it literally just by voice. So if you want, so your value added to this field is going to be something like that. Okay, I can understand what's going on behind the scene. I'm an expert, right? So I have this analytical tools in my arsenal now that I can interpret things. Because to be honest, guys, at the end of the day, you can use PyCaret, and PyCaret is going to run 24 different time series models behind the scene, and it's just 3 lines of code, right? And then you might start scratching your head. Okay, I know all these, I heard all these names, but I don't know what are they doing. So that's why I want you to just be patient with me, right? So maybe the future lecture videos are going to be just like these ones, heavily theory, but just bear with me because I think there's value here, and the value is that you understand the theory behind these models, right? Because again, application-wise, Python is going to become easier and easier and easier down the road. Okay, until the next one, take a good care. I'll see you later. If you're looking to stay updated with the latest versions of the course's materials, please make sure to follow my GitHub and remember to refresh your repositories periodically. If you find yourself needing a bit more background in econometrics, machine learning, or deep learning, check out my other YouTube videos for additional insights. And for all the latest news and quick updates, don't forget to follow me on Twitter. Thanks for joining me, and let's keep learning together.